Back in episode 1, we watched a window slide along a stream, carrying only the most recent symbols. The engram model is the most literal thing you could possibly do with that window. You count. The name just means we look at short runs of a few symbols at a time. A run of 2 is a bigram, a run of 3 a trigram, and the window holds the context those runs share. Here is a tiny stream over just 2 symbols, the symbol A and the symbol B. Alongside it, we keep a small table of tallies, one cell for every context paired with every symbol that might follow it. Right now, every cell is 0, because we have not looked at the stream yet. Watch the window slide along the stream, exactly as it did last episode, but this time each step leaves something behind. Look at the symbol inside the window and the symbol that comes right after it, and add 1 to the counter for that pair. The first context is the symbol A, and what follows is the symbol B, so that counter ticks up to 1. Slide forward and keep going. Each new position is another context paired with whatever came next, and every pair bumps its own counter. Notice that one cell never moves. The symbol A is never once followed by the symbol A again in this stream, so its counter stays at 0. Hold on to that 0, it will matter more than you would think. When the window reaches the end, all that remains is this little table of tallies. And that table is the entire model. No training, no tuning, just counting what actually happened.
A wall of tallies still is not a prediction. How do I turn those counts into the probability of the next symbol?
You normalize. Take one row of the table, say every time the context was the symbol B. Count how many times each symbol followed, and divide by the total number of times that context appeared. In our stream, the context B was followed by the symbol A twice, and by the symbol B once, 3 visits in all. So the probability of a given B is 2/3, and the probability of B given B is 1/3. Every row becomes its own little probability distribution over what comes next. That ratio, the count of the pair over the count of the context, is called the maximum likelihood estimate. Why call it maximum likelihood? Because of all the ways you could set those probabilities, this ratio is the one that makes the data you actually saw as likely as possible. And it has a lovely property. When a context appears often, its ratio settles down and closes in on the true probability behind the stream. This is just the law of large numbers doing its quiet work. Average enough independent outcomes, and the average stops wandering. With 1,000 visits to a context, a count near 600 tells you the odds are close to 60 in 100, and more data only sharpens the estimate. So while the counts stay dense, plain counting is not merely simple, it is genuinely excellent. The trouble begins exactly where the counts run thin. Look again at that stubborn 0. Maximum likelihood is blunt about it. The probability of the symbol A following the symbol A is exactly 0. But 0 is the strongest claim a model can make. It does not say unlikely, it says impossible and impossible for all time. We saw all of 7 symbols, and on the strength of that the model has sworn that one particular pair can never occur. With longer contexts, it gets far worse. Remember the sparsity we mentioned. Widen the context, and the number of possible contexts explodes. Most of them never appear in your data at all, so their whole row of counts is nothing but zeros, and you cannot even form the ratio. It would be 0 divided by 0. The perfectly reasonable sentence you are trying to predict grinds to a halt on a context nobody happened to write down. Unseen does not mean impossible. But counting alone cannot tell the difference.
Is a single 0 really so dangerous? Surely one wrong probability just washes out.
It does not, and here is why it is fatal. Recall how we scored a predictor back in episode 1. Your surprise at each symbol is the negative logarithm of the probability you gave it. Feed a probability of 0 into that score, and the logarithm runs off to infinity. So the moment a symbol you called impossible actually arrives, your surprise is infinite. and your total log loss is infinite too, no matter how well you predicted everywhere else. The compression view says the very same thing in bits. To encode an event you swore had probability 0 would cost infinitely many bits. 1 0 in the wrong place, and the whole model is worthless. A predictor may never be completely certain. So we need to leave a little probability for the things we have not seen. The oldest fix is add 1 smoothing. Due to Laplace, before you count anything at all, pretend you have already seen every possible pair exactly 1 time. Now every cell starts at 1 instead of 0, no probability is ever exactly 0, and the catastrophe is gone. The stubborn cell for the symbol, A following the symbol, A now holds a small but honest chance, rather than a flat impossibility. It is crude, though. Adding 1 to everything steals a lot of probability away from the events you genuinely observed, and it assumes every unseen pair is equally likely, which is rarely true. It trades a fatal flaw for a merely clumsy one. We can do better.
Better how adding 1 everywhere feels like a hack.
It is. The better idea uses something we have been ignoring, the shorter contexts. Suppose you are predicting the next word after 3 particular words. If you have seen that exact 3-word context, wonderful, trust it. But if you have never seen it, do not give up. Drop the oldest word and ask the 2-word context instead, and if that too is unseen, fall back to a single word. This is Backoff. Fall from a long context to a shorter one until you reach ground you have actually stood on. Its close cousin, Interpolation, does not choose at all. It blends the predictions from every context length together, weighting each by how much you trust it. Long contexts when you have the data, short contexts when you do not. That single instinct is the heart of every good model that predicts by counting. Before we move on, let us give n-grams their due. They are wonderfully simple. Count, divide, and smooth, all in a single pass over the data. They are fast, they are easy to store, and they are transparent. You can point at any number and say exactly where it came from. For decades, this was the workhorse. Speech recognizers, machine translation, spelling correction, and the early text compressors all ran on counted n-grams. When you have plenty of data for the depth you care about, they are still very hard to beat. N-grams are the strong classical baseline, the honest yardstick every fancier method has to clear. But there is a wall, and it has 2 bricks. First, you must fix the depth in advance. You choose to look back 2 symbols, or 3, or 4, and that one depth is applied to every context alike, whether or not it is the right amount of memory for that particular history. Second, the contexts multiply. Each extra symbol of memory multiplies the number of possible contexts by the size of the vocabulary. Over English words, a 2-word context already runs into the billions of possible contexts, and a 3-word context into the hundreds of trillions, and almost all of them stay empty. Smoothing patches the holes, but its weights are set by hand, not learned. The model never discovers, for each context on its own, how far back it should actually look. And that last sentence is the doorway to the next episode. What if you did not have to pick a single depth, or tune the weights by hand? What if, for every context, you quietly kept a model of every depth at once, and let the data itself decide how much to trust each one? Back in episode 1, we teased tree sources, contexts that stop at their own depth. The method that makes them practical is context tree weighting. And it does exactly this. It averages over all context depths and learns the right blend, per context, with provable guarantees. It is what n-gram smoothing has been clumsily reaching for all along, done optimally. Stop choosing a depth and start weighing them all.